So today we're going to be doing 8.1, which is going to be unions and intersections. So this is your real introduction to probability. You kind of get introduced to probability in middle school. You do basic probability, right, like coin flipping and dice rolling. But this takes it to another level, utilizing mathematical notation. So we are going to be utilizing those concepts as well, the ones that you learn in middle school, but we're going to be adding to that another layer, basically. So we have to talk first about what a set is and why it's important. So far in this class, when we do Unit 5, we talk about sequences and series, okay? A sequence is a set of numbers that follow a pattern, right? So either adding 3, subtracting 3, multiplying by 3, something like that. And a series is where you take the terms of a sequence and add them up. Now a set, our third S in math, is just a set of numbers. And the thing about a set doesn't have to have a pattern. And it doesn't even need to be in order. It's just a collection of a bunch of numbers. Now, two important things you need to know about a set is that the numbers do not need to be in order, but we preferably will write them in order. And you do not need to write the same number twice. So if you end up putting two numbers, like a 1 and a 1 in a set, you only have to write it once. So those are two important things. And then we have what's called a universal set. So this is the set of everything we are interested in. So if we're talking about 3 separate sets, and we're going to be talking about unions and intersections of those 3 sets, the universal set is a collection of everything all the sets have. So as you can see here, we have 3 sets. We have A, B, and C. The universal set, known as U, is basically where we take all 3 sets and combine them together. Everybody see that? An element indicates the membership or belonging to of a set. So we use this little symbol. It kind of looks like an E. So 2 is in the set A, but it's not in the set C. Does everybody see why that's true? So 2 is in set A, but is not in set C. We use a little slash to indicate that it's not in that set. And then a subset is a set whose entire elements belong in another set. So for example, every element in A is in B, okay? But not every element in A is in C. So this is kind of like a real world scenario of this would be like, there's a set of all the cars in the world, and a subset of that is all the cars that are Honda. Okay, that's kind of like what that means, right? So keep that in mind, what that means. So in order to be a subset, your entire set has to fit inside that set. So if I said, for example, I don't know, we'll think of another example as we go on that would exclude it from a set. So intersection is the set of elements found where the sets overlap. So we use the term and for this. So when you see and, we're talking about intersection. So this is basically what the 2 sets have in common, and we use this upside down U shape to talk about that. So what does set A and B have in common? What 2 numbers? 1 and 2. That's where that comes from. And then what does sets B and C have in common? 4. A union is where you take both sets and combine them. So we don't care what they have in common. We're just simply combining the sets. So if we take set A and set C and combine them, we end up with 1, 2, 4, and 5. Now, if you combine 2 sets that already have elements that they share, you don't have to write that number twice. So for example, if we combined A and B, it would just be 1, 2, 3, 4. A complement is all the elements that are in the universal set that do not belong to the named set. So there's 3 different terms or like notations that we use for complement. You can either use this little, basically like an apostrophe, or you can use this squiggle or a little C. They all mean the same exact thing. So this is everything in the universal set that is not in set A, which is 3, 4, and 5. Does everybody see where the 3, 4, 5 came from? It's everything in the universal set that is not in set A. And then the empty set is when we end up with nothing. So for example, if we were trying to find the intersection of A and C, do A and C have anything in common? No, so that would be nothing in the set. So there's 2 proper ways to write that. You can either simply write brackets with nothing in them, or you can write a 0 with a line slash through them. Those are the 2 notations that you have the choice of using. Multiple choice can use either. So let's go ahead and get started on some examples. Let's talk about sets and elements so we can get a better grasp of what this means. So we want to find a set that has the elements that are the months that begin with the letter J. So we're going to call this set J, and we're going to identify the elements of set J. So What is the first month you can think of that begins with the letter J? Good, January. So January is an element in the set of months that begin with the letter J. And what would be another element of that set? June. And are there any other elements of that set? July. So those would be the elements of the set. And those would be the total number of elements. And this is what we call a finite set. Why is this set finite and not infinite? It doesn't go on forever, right? Good. So now we're going to talk about the set of whole numbers. So if you don't remember, we have several different sets of numbers that we talk about frequently. We have integer set, irrational, rational number set. Whole number set is basically all whole numbers that are non-decimal, that are bigger than, that are basically non-negative. Non-negative counting numbers. So what's the smallest non-negative number you can think of? Even smaller? 0. And the next whole number after 0 would be what? 1, 2, 3. And what's the issue with this set? It's infinite. You're right. Infinite. So it goes on forever, right? So we don't want to write this forever. So what we're going to do is we write about 5 or 6 terms. We put a comma, and then we put 3 dots. And those 3 dots indicate to the person reading this that this set goes on forever in the same pattern. So once you've established that a pattern exists, you can put the dot, dot, dots to indicate that it keeps going, following that same trend. And then the next one, we'll do even numbers between 11 and 23. We're going to call this set E for even numbers is equal to. What's the smallest even number between 11 and 23? Good, 12, and then it would be 14, 16, 18, what else? 20 and 22. Would I keep going? No, because then we'd exceed 23, right? So is this set infinite or finite?
Would you have a bracket or one like that?
You still use the brackets. The indicator when you use infinite is when you use the dot, dot, dots. So that's the difference that you would see here. So you use the dot, dot, dots when it's infinite. And when it's finite, it just simply ends on a number. Any questions about that? Yes.
Why is it not infinite?
This one, why is it not infinite? Because, yeah, it's between 11 and 23. Does that make sense? Okay. So directions, determine if the statements are true or false. So this is what we call subset notation. So that means, can this set completely fit inside this set? So I like to think of it literally. So say we took all of the Oviedo High School teachers and we put them in the gym, right? And we had circles on the floor for each subject they teach, and they would stand in those circles, right? Those would be the subsets. Would the Oviedo math teachers completely fit in the subset of Oviedo teachers? Yeah, they would fit. There wouldn't be any leftovers that wouldn't fit in that set, right? There wouldn't be anybody that wouldn't be in the gym at all. We'd all fit inside of. So basically, we're a subset of the Oviedo teachers. Does that make sense? We're underneath that umbrella. So if we took the Oviedo High School basketball team and we put them in the gym, could we make a set of those people that were the quarterbacks? No, why not? Different sports. So that is not a subset of the basketball team because it wouldn't include the same people, right? Does that make sense at all? Am I explaining this well enough? Okay. If we took a list of all the Oviedo High School math courses, would Algebra 2 be an element of that set? Yeah. Yes. If we took the set of numbers 0 through 10, are the even numbers of that set a subset of it? Yeah. Because they're all these numbers are included in this set. There's no extra ones. If we took the set of prime numbers, what are prime numbers? Anybody remember?
Numbers that can only be multiplied by one of themselves.
You're almost right. Divided by one of themselves. Good. So like for example, 1, 2, 3, 5, 7, 11, 13. Those are some prime numbers. They're numbers that are only divisible by 1 in itself. They're not divisible by anything else. Now, what are some examples of odd numbers?
7.
Good. So like 1, 3, 5, 7, 9, right? So odd numbers. Are all odd numbers prime?
Not all of them.
Not all of them. So is it a subset?
No.
No. Every element of this one has to be in this one in order for it to be a subset. See how there's some examples of odd numbers that are not prime numbers, which means it's not a subset. And now we're going to look at this one. So if we look at algebra 2, are math courses an element of algebra 2? No. It doesn't go the other way around. Well, algebra 2 is an element of Oviedo High School math courses. It's not the other way around, right? We just take algebra 2. Oviedo High School math course is not an element of algebra 2. It's the other way around. Does that make sense? Kind of? I don't know. You guys tell me if you need a better explanation. But is everybody good with this page? Are we ready to move on? All right, so now we're going to talk about intersection and union. Excuse me. So, this is an intersection, okay? And this is a union. And we're going to talk about the difference of the two. Just so you have an idea, maybe that'll help you so you remember. Union looks like a U, so that's the way I usually remember it. So intersection is what the sets have in common. So what do these two sets have in common?
8.
They have an 8, but they also have a 7, 8, and a 9, right? In common. So that's what the two sets have in common. Everybody see where I got those from? And then union is simply taking the sets and merging them together. So taking all the elements from A and adding in all the elements of B. So basically you're going to list all of the elements. And notice that while both sets had 7, 8, and 9, I didn't write it twice because it's unnecessary. Okay? So you merge them together, so it's what they have in common, and then combining. So everybody see the difference between an intersection and a union? Okay.
So intersection is just one thing and then union is both?
Yeah, so intersection is what they have in common. So let's try the next one. So this is intersection. What do these two sets have in common? Nothing. So we can either write the empty set or we can write the 0 with the slash through it. Your choice. It's good to know both because you never know what a multiple choice question will give you. And then if we take the two sets and merge them, it's just going to be 1, 2, 3, 4, 5, 6. So that's merging the two. Now, you don't need to write them in order. You're still correct if they don't go in chronological order, but you should get in the habit of writing them in order. It's easier that way. Okay. So do we have any questions about that? All right, let's try the next one. So what is this? I'm looking for what the sets have in common, which is what?
5 and 10.
Good, 5 and 10. And the next one, we're just merging the two sets together. So 5, 6, 7, 8, 9, 10, 15, and 20. So merging the sets versus finding what they have in common. So do we have any questions about that so far? So now we're going to get into visual representations of sets and how it can help us figure out the math, okay? So let's talk about some of these visual representations. We often use Venn diagrams. So who in here has heard of a Venn diagram? Have you used a Venn diagram before? Probably in other classes, right? And typically you use the Venn diagram when you're looking for things that have that are in common, right? So it's a visual aid to determining probabilities. So when adding data, we always start the innermost section and work outwards. So that's very important. You always start inward and work outward, okay? So we're going to use that really a lot in this lesson. So just make sure you understand and remember that concept. So let's talk about how we deal with these. So typically you're going to see these in a box. And this box is just the universal set. It's the elements that are in both sets. And it just kind of encapsulates it. So subset. A is a subset of B. So let's say we have the set B, and A exists completely inside of it. There's nothing in A that is not in B, which is why it's completely inside. So that's like the example I said with the cars. If B is the set of all the cars in the world, A would be a subset of that. So like Honda, or like Toyota, whatever company, or even it could be like all trucks are cars or something like that. It's completely inside. There's no element of A that is not in element B. The next type we'll look at is union. So if you take the set of A and you take the set of B, this is where we take them and just combine them, okay? So basically, it's every element in both, okay? So the overlap, it just takes up the whole thing, the shaded region. So this is like if we just took sophomores and juniors and put them all in the gym. We're just combining the two groups together. Now intersection is what these two sets have in common, right? So this is like if we took the sophomores and the juniors and all of the students who are in Algebra 2 sit in the middle. See what I'm saying, how they have that in common? That would be all the Algebra 2 students that are in 10th and 11th grade, and then this would be all the 10th graders who are not in Algebra 2 and all the 11th graders who are not in Algebra 2. Now the complement is everything except for that one thing. So say we took all the cars in the world. Say you wanted to buy a car and you really hated a specific brand, okay? You're like, I'm okay with any car except for Ford or something. That would be excluding that one group. Does that make sense? So that's what the complement looks like. So now let's talk about visual set of relationships, and we're going to make our own Venn diagram. Excuse me. So it says, given the universal set A and B, we have set A and we have set B, and they want us to complete a Venn diagram and use it to answer the following. So when you're dealing with these type of problems, it's really helpful to do the Venn diagram. Now I want to mention what they mean by the universal set. See how they just said A and B? What do you think that means? It means that the universal set contains what? Everything that A and B contain. So just for the sake of simplicity, I'm going to write out what the universal set is this time because I want you to kind of get the grasp of it. So this is everything the universal set contains. This is just a simpler way of saying that. It contains everything A contains and everything B contains. So the way we do our visual representation is we put a U here on the outside. This is the universal set. It contains everything. And then here is going to be A and B. Now this section right here, the overlap, is basically the intersection of A and B. So that's what they have in common, right? So that's what we always start with. We work inside out. So what do A and B have in common? Not quite. 13 through 15, good. So A and B have 13, 14, and 15 in common. Does everybody see why that goes in the middle? And then what would you think would go over here? What A has that B does not, right? So 10, 11, and 12. Why don't we list 13, 14, 15 over here? Yeah, good. So think of this right here. A is this complete circle. We've already listed 13, 14, 15 inside of A, but it's just also in B. So we list what A has that B doesn't over here, what they have in common, and then what will we list on this side over here? What would go in this part? Which is? Good, 16 and 17. So now that we have our visual representation, and as you can see, the universal set contains everything. It's basically it's like everything inside is contained. So what does this mean with this little symbol? It's what A does not have, right? So the list of what is not in A. So which numbers are not in set A? 16 and 17. So that's everything that A does not have. Everybody see how we got that? Next one. What is not in set B?
10, 11, 12.
Good. 10, 11, and 12. See how B is this whole circle? And what's not in B is 10, 11, and 12.
What does B mean the same thing as A?
Good question, yes. So, see that symbol right there, the little prime, the C, and the squiggle all mean the same thing. They're just three different ways of saying the same thing. So we use all three to expose you to what they could use on, standardized tests. So this right here is the intersection of A and B. That means what they have in common, which are what three numbers? Good, 13, 14, and 15. So now, here's where you have to kind of utilize your algebra skills of order of operations. You have to do parentheses before you do the outside of the parentheses, right? So we have to find the intersection of A and B and then find the complement of it. So we've already found the intersection of A and B. So that's everything in the universal set that's not in the intersection of A and B, which is what? What's in the universal set that is not in the intersection of A and B?
16, 17, 10, 11, 12.
Good. So 10, 11, 12, 16, and 17. So that's everything that is not in the intersection of A and B. So everybody see how we got that? Now this one here, see how there's no parentheses? This means that you're finding the complement of B and then finding the union of the complement of B and A. So I like to actually list these out sometimes underneath to help me out. So let's talk about the complement of B. What's the complement of B? It's everything that B does not have, right? What does B not have that's in the universal set?
16, 17.
B has 10 and 11 and 12, right? So B does not have 10, 11, 12. That's the complement of B. Does everybody see how I got that? 10, 11, and 12. It's what B does not have. Hang on. Let's wait for the annoying bell to go. D is what the intersection of A and B did not have. See how this is what the intersection had? This is what it didn't have. So this one here is what B does not have. See how B doesn't have 10, 11, and 12? The union of that and what A does have. So what does A have? All this stuff. Well, A has all this, right? And union, is the union where we find what they have in common or when we merge them? Merge. So now you're simply merging these two sets together. So it's just going to be 10, 11, 12, 13, 14, and 15. You're just merging the two sets.
So you're merging what B doesn't have in set A.
Correct. Thought we were done with the bells. Just kidding. More bells. Okay. Now we're going to find what A does not have. What does A not have?
16, 17.
Good. A does not have 16 and 17. We're going to take the intersection of that and what B does have, which is 13, 14, 15, 16, and 17. So intersection means what they have in common. What numbers do these two sets have in common?
16, 17.
Good, 16 and 17. So are you starting to get the idea here of what happens with these? Understand the complement, what it means? Okay. It's basically the opposite of what it has. So is everybody ready to move on to the next one? Okay. So we're going to do this problem, and then after lunch we're going to do example 3. So this is the last one we'll do before lunch. So this is where we use probability in a real world situation. So it says 2 Scoops Ice Cream is testing out 2 new flavors, chocolate cherry and raspberry ripple. 2 Scoops found that 32 customers liked chocolate cherry and 58 customers liked raspberry ripple. 12 liked both flavors and 47 liked neither. find the probability that a randomly selected customer, and then we're listing out these several different probabilities. So the first thing is you always work inside out. So you're going to work inside. So this is what represents people who like both flavors, right? In this overlap region, does everybody see why that would represent what they both like? So how many people like both? 12 people like both, right? So we've dealt with that. They like both flavors. And then where would the 47 that liked neither go? On the outside, good. Because that's like if we put everybody in the gym and we put these literally on the floor, people would have to stand in either 3 of those parts of the circle or the outside. Those are the people that wouldn't stand in anywhere in the circles. So now we have to do a little bit of math here. So it says here, 2 Scoops found that 32 customers liked chocolate cherry. So 32 customers liked chocolate cherry, but what's the problem? We already have 12 of those customers already in the circle. So what do we have to do to find what goes here? Subtract. So what's 32 minus 12? 20. So now, as you can see, the circle for chocolate cherry now has 32 people in it. Does everybody see how we got that? Subtract. 32 minus 12. Now the circle has 32 people in it. Because we already had 12 people in the circle. Now for the next one, 58 customers like Raspberry Ripple. We already have 12 people in the Raspberry Ripple circle, so what do we have to do? Subtract from 12 from 58, which is 46, right? So that's how you fill in the circle. And then how could we find the total number of customers? Good, we add up all 4 of these, and when you do that, you get 125 total customers. So if we're talking about the probability of things happening, that's always going to be out of 125 people, right? So think of like a coin toss. What's the probability of getting tails? 50%, which is 1/2, right? Because that's one choice out of 2 options, right? What's the probability of rolling a 3 on a die? 1 out of 6, because there's 6 sides, right? So it's out of how many people there are this time. It's out of 125 people. That's what that's what's going to be the denominator in all of these. So, out of 125 people, how many of them like both chocolate cherry and Raspberry Ripple? Good, 12 people. Out of 125 people, how many of them liked only chocolate cherry? 20. Out of 125 people, how many of them liked only Raspberry Ripple?
40.
Good. Out of 125 people, how many of them do not like chocolate cherry or Raspberry Ripple? 47. Out of 125 people, how many of them liked chocolate cherry in general? 32. So it didn't say they only had to like chocolate cherry, it's just that they liked it. So anybody who falls in the circle likes the flavor. Okay, do you see the difference between likes only that and just likes it? Okay. And then out of 125 people, how many of them like Raspberry Ripple? 58. So that's the difference between liking it and only liking it. Out of 125 people, how many of them do not like chocolate cherry?
93.
Good. How'd you get that?
46 was 47.
Good. Good job. So to find out how many people do not like chocolate cherry, you have to add up how many people didn't like either and how many people just liked the Raspberry Ripple, right? So to get that, if you're wondering, that was just 46 plus 47. And then out of 125 people, how many of them did not like Raspberry Ripple?
67.
Good. 67, which comes from 20 people who liked just the chocolate cherry and the 47 people who liked neither. Does that make sense? So this is how you could write the probability out of 120. You could say 12 out of 125. But oftentimes, probability is represented as a percentage. So to find the percentage, and I'll show you how to do one of these, and you can do the rest of them. You're going to do 12 divided by 125 times 100. And that will convert it to a percent. So 9.6% people liked both. So I'm actually going to write these in the box. So 9.6% is this portion. And then 20 divided by 125, that's going to be 16%. 46 divided by 125, that's going to be 36.8%. And then if we do 47 divided by 125, that's going to be 37.6%. That's this portion out here. Now, what would happen if I added up those four percentages? What should it equal? 100, because that would encapsulate everybody who were surveyed, right? Now you could calculate the rest of the percentages using the same method. And then when we get back from lunch, we'll do a three-piece Venn diagram. It would equal 100 or 125? It would equal 100%, because that would in total everybody, 100% of the people.